It is essential for first responders to know how to create memory dumps in order to secure important evidence that may be stored in a device's memory. Hi, my name is Roy Borgen and I'm the founder and CEO of ShieldTech. When incidents occur, system administrators, DevOps personnel and other employees who are not usually involved in incident response are focused on getting systems back to their normal operation. In that process, they will often delete virtual machines, Kubernetes pods, and restart systems, causing the loss of potential evidence stored in the device's memory. This can result in the loss of important evidence, causing potential serious consequences for the company, leading them to not fully understand the extent of the compromise. It is important that first responders are trained in securing memory dumps so that it is available for further analysis in the future. By learning how to create memory dumps, first responders can take proactive steps to help their organization protect crucial evidence so that they can fully understand and address any potential security breach. In this lesson, we'll be looking at memory forensics. We'll start out by looking at what it is, and moving on to talk about the importance of documenting the system time on systems where you collect evidence. We will talk about how to do memory forensics on Windows, Linux, and Mac. We'll also provide a demo on how to do this on Windows and Linux. We will unfortunately not be demonstrating this on Macs. The reason for this is that there are no widely available open source tools for performing live memory forensics on newer Mac systems. Memory forensics is a branch of digital forensics that deals with the acquisition, analysis, and interpretation of data stored in a computer's memory, RAM. It is a crucial aspect of forensics investigation, as it allows analysts to extract and examine evidence that may not be available through other means. Memory forensics involves the use of specialized tools and techniques to extract and analyze data from a computer's memory dump, which is a snapshot of a system's RAM at a specific point in time. This data may include information about running processes, network connections, open files, and other system activities that may be relevant to the investigation. When a computer is turned off, much of the data stored in RAM is lost. However, if a memory dump is taken before the system is shut down, it will allow analysts access to this otherwise lost data. In addition to its forensics application, memory forensics is also used for incident response and malware analysis, as well as for troubleshooting and performance optimization. Before we begin the process of collecting evidence from memory, it is important to document the system time and time zone settings on the device. This is because the system time may be lost or modified during the memory collection process, and it's essential to preserve this information to provide context and understanding about when the events in the gathered evidence occurred. This is of course also important if our case were to end up in a court of law. If there is doubts about when events occurred, this might result in the dismissal of the case. Let's start off by looking at how to document system time in Linux and Mac. Both of these operating systems have a built-in tool that can be used. This is done using the date command. Let's have a look at a quick demo on a Linux system. First, log on to the system. Once logged in, we can fetch the system time and time zone using the date command. We can store this information into a file by running the date command space bracket space and the file name, which is this case system_time.txt. This will create the file system_time.txt in the directory we are located in. If we examine the content of the file by running cat space system_time.txt, we will see the file's content. The next step is to create a checksum of the system_time.txt file. This is done by running SHA-256-sum space system_time.txt. Make note of the checksum and copy the file to store it as evidence. Once the file has been copied, it's important to verify that the checksum is correct and that the file is intact. In Windows, the process is similar. Windows has built-in PowerShell commands that help us display the date and time and the time zone settings. These PowerShell commands are getDate and get time zone. Let's have a quick look at a demo of how to collect this on Windows. First, we need to log on to our Windows system and open up PowerShell. Once we have PowerShell open, we enter the getDate command, followed by double brackets and the name of our output file. The double brackets will redirect the command's output to the file we specify. In this example, we name the file system_time.txt. We will then enter the command getTimeZone, followed by double brackets and the same file name, system_time.txt. This redirects the command's output to the file. The double brackets means that the command's output will be appended to the file, so it doesn't overwrite any of the existing content. If we were to use a single bracket, the content of system_time.txt will be overwritten. We can output the content of our file system_time.txt by using the type command. As we can see, the file contains the current time and date and the time zone settings. Once we have secured this information, it's important that we generate a checksum of the file. This can be done using the PowerShell command getFileHash followed by system_time.txt. Make a note of the file hash, copy the file, and regenerate the file hash once the file is copied. This to verify the integrity of the secured evidence. We will now look at how to create a memory dump in Linux. For this we will use a tool called AVML. Acquire Volatile Memory, AVML, is a tool used to collect and analyze the volatile memory, RAM, of a computer system running Linux. It is written in the programming language Rust and is intended to be run as a standalone binary file. One of the key features of AVML is that it can be used to acquire memory from Linux systems without requiring prior knowledge of the specific operating system, distribution, or kernel being used. This means that it does not require on-target compilation or fingerprinting to work. This is important as we want to make as few changes as possible to the memory of the system in order to preserve evidence. As of January 2023, AVML is tested and confirmed working on the following distributions. The process of gathering evidence using AVML is described in this slide. First, we need to download AVML to the system we want to secure memory from. Optionally, we can transfer it using a USB thumb drive. Once we have the tool on the system we want to secure memory from, we need to ensure that the user has permissions to execute the application. Once we have changed permissions, we will execute the binary with root privileges. When the collection process is completed, we need to change permissions on the memory dump file in order to make it readable. We will then create a checksum of the file before we copy it to a secure storage location. Once the file is copied, a checksum will need to be regenerated in order to verify the integrity of the secured evidence. Let's have a look at a demo of this. AVML can be downloaded from Microsoft GitHub page. Yes, Microsoft has developed a tool for securing memory from Linux systems. The web address is shown in the address bar, but it's also available in the written documentation that goes with this lesson. Navigate to Releases, shown here in the lower right corner, and download the latest AVML binary. It is important that we don't clone the repo and build the application on the system itself. We want to limit our impact on the system as much as possible in order to preserve evidence. Log on to the system you want to secure the memory from. Note that I have already downloaded AVML in this demo. If we run the command ls-la, we can see the presence of the file. Notice that the file AVML is not executable. We need to change this using the chmod command. We enter chmod 755 AVML. If we do ls-la again, we can see that the permissions has changed. Next step is to execute AVML with root privileges. we enter the command sudo:/avml memory.dmp. Memory.dmp is the name of the memory dump generated by AVML. AVML will now start dumping the memory into the file. The command does not give any verbose information to the console, and the time this takes can vary, as the file generated will match the size of the memory on the system. So just because you don't see any output does not mean that there's anything wrong. Once the command is done running, we can use ls-la to verify the output. We can see that the file memory.dmp has been generated. Notice that root is the only user that has permission to the file, and the permissions are read and write. We'll change the permissions using the chmod command. The command needs to be executed with root privileges. Now that the permissions have changed, we can generate a SHA-256 sum of the file. We'll enter the command SHA-256 sum memory.dmp. It is important to make a note of the checksum and copy the file to a secure location. In order to ensure the integrity of the secured evidence, the checksum should be verified once the file has been copied. When capturing memory dumps from Linux systems, it's often necessary to create a volatility profile to properly analyze the dump using the Volatility Framework. The Volatility Framework is an open source collection of tools for analyzing and extracting information from volatile memory RAM dumps. It is commonly used in the field of digital forensics to analyze data from memory of computer systems, either as part of an investigation or for incident response purposes. The Volatility Framework is designed to be extensible and modular, with many plugins available to analyze various aspects of a memory dump, such as running processes, network connections, and open files. The volatility profile is a set of configuration data that tells the volatility tool how to interpret and analyze the memory dump. It includes information about the specific operating system, kernel version, and hardware architecture of the system from which the memory dump was taken. The reason for creating a volatility profile is that the structure and data layout of the memory dump can vary significantly depending on the specific system and configuration being used. A volatility profile allows the volatility tool to understand the specific layout and organization of the data in the memory dump and extract meaningful information from it. Without a volatility profile, it may be difficult or impossible to accurately analyze the memory dump using volatility. For this reason, it is wise to create a volatility profile when capturing the memory dump. Let's have a quick look at the process of doing so. The first step is to download volatility or copy it from a USB thumb drive. Once it's downloaded or copied, we need to unzip it. Once it's unzipped, we need to install the required packages to run it. Once the required packages is installed, we need to compile it on the system we captured the memory dump from. We'll do this by executing the make file. Once we compile the profile, we need to zip it together with the kernel symbol map file. We've now created a volatility profile. This profile should be stored in evidence, so we'll create a checksum and copy it. Once the profile is copied, we'll verify the checksum again. Let's have a look at a demo of this process. Volatility can be downloaded from the Volatility Foundation's webpage, www.volatilityfoundation.org. Optionally, you can clone the GitHub repo on github.com/volatilityfoundation. I will be demonstrating how to git clone. Once you're in the Volatility Foundation's webpage, navigate to Downloads. From the Downloads page, choose to download the volatility source code. Let's jump into our Linux demo machine and create a volatility profile. Note that I'm in this demo running Debian, so if you're running a distribution with a different package manager, the installation will be different. We'll start off by installing Git using the apt install git command. Once Git is installed, we'll clone Volatility's Git repo by running the command git clone https://github.com/volatilityfoundation/volatility.git. If we now run the ls command, we'll see that Volatility has been installed in our home folder. Next step is to install dependencies. We'll do this by running apt install build-essentials linux-headers $parenthesis uname space -r parenthesis space dwarves space dwarf dump. Once installation is complete, we'll navigate to volatility/tools/Linux. If we run ls, we'll see that there is a makefile in this folder. Makefiles are used for compiling source code files into executable programs. Using makefiles simplifies the build process, since it allows developers to automate the build process and avoid manually typing long and complex compilation commands. Instead, in order to start the compilation process, you can just run the command make. Let's do that now. Once the compilation is complete, we'll execute zip by running zip space $ parenthesis lsb_release space -i space -s parenthesis _ parenthesis uname space -r parenthesis _ profile.zip space module.dwarf space /boot system.map $, parenthesis uname space -r parenthesis. This will create a zip file with the name of the distribution you're running and the version, and inside that zip file it'll put module.dwarf, which was created when we ran the makefile, and the kernel symbol map. This zip file makes up the volatility profile. Although it is not required, it is good practice to name the zip file after the distribution name and the kernel version. The profile is stored as evidence, so the next step is to create a SHA-256 sum of the profile. The profile is copied and stored as evidence in a secured location. Make a note of the SHA-256 sum and re-verify it after the copy. Let's have a look at how to do this in Windows. For Windows, the process is a little simpler, as we do not need to create the volatility profile. To create a memory dump, we'll use a tool called WinPmem. This tool works in a similar way as AVML and allows us to copy the entire physical memory of a machine and save it to a file, which can later be used for analysis using the volatility framework. The tool can be used to extract data such as artifacts left behind by malware, or to perform memory analysis to extract information about a system's state at a specific point in time. WinPmem is developed by a company called Velocidex. Velocidex is known for developing and maintaining several forensics tools. Let's examine the steps required to create a memory dump in Windows using WinPmem. First, we need to download WinPmem or copy it from a USB drive. Once this is done, we'll open up a command line as administrator and execute WinPmem. When the collection process is completed, we'll create a checksum of the evidence, copy the memory dump, and verify the checksum to ensure the integrity of the evidence. WinPmem can be downloaded from GitHub by navigating to github.com/velocidex /winpmem. Click on the latest release in the lower right corner and scroll down and download either the 32-bit or the 64-bit version, depending on the operating system you're securing the memory dump from. Once the file is downloaded, open up a command prompt and run it as an administrator. You can do this by clicking the Start menu and typing cmd and choosing Run as Administrator on the right side. Navigate to the location you downloaded the file to. Execute the application by running winpmem_mini_x64_rc2 space memory.raw. In this case, memory.raw is the output file of the application, meaning that this is the file that will contain the memory dump. The execution time will vary depending on the memory size of the system. Once the execution is completed, we can see that we have a new file created in our directory called memory.raw. Before we copy the file and store it as evidence, we need to create a SHA-256 sum of it. We'll do this by running certutil-hashfile memory.raw space SHA-256. Make a note of the hash value, copy the file, and store it in a secure location. Verify the hash value by regenerating it to ensure the integrity of the evidence. There are currently no widely available open source tools for performing live memory acquisition on newer Mac systems. These are systems running the latest Apple Silicon ARM-based processors. These are MacBooks that came out in 2020 or later. Some commercial tools may be able to perform this task, but it is likely a complex and technical challenging process that requires specialized knowledge and expertise. This, however, might change in the future. This section will provide a guide on acquiring memory from Mac devices pre-2020. The process involves using a tool called OSX-PMEM. The tool is developed by Velocidex. OSX-PMEM can be downloaded from GitHub. You find a link to the GitHub page in the PDF attached to this lesson. Once the tool is downloaded or copied using a USB stick, it needs to be unzipped on the targeting machine. In order to execute it, you need to change permissions to it, making the binary file executable. Once permissions have been changed, the tool needs to be executed using root privileges. Once the memory acquisition process is completed, a checksum of the output file must be generated. The file can then be copied to a secured storage location, and checksum needs to be regenerated to verify its integrity. We will not be demoing this in this lesson. However, a guide is created in the PDF containing the written documentation for this lesson. In this lesson, we provided an overview of the process of creating a memory dump, as well as the importance of securing it as evidence for further analysis. Memory forensics is not only used for forensics investigation, but also for incident response and malware analysis, as well as for troubleshooting and performance optimization. By following the steps provided in this lesson, first responders can take proactive steps to protect crucial evidence before putting in place corrective measures. This will better equip the organization to fully understand and address potential security breaches. Remember, the accuracy and completeness of the memory dump is at utmost importance in any forensics analysis, so always be sure to follow best practices and validate your data acquisition methods. That concludes this lesson on volatile memory acquisition. I hope you found this lesson useful. Hopefully we've shown that it doesn't take much to secure memory from a Linux or Windows device, and that you implement processes in your organization to ensure that first responders take the appropriate steps to secure volatile memory from devices. If you have any questions, please email us on info@shieldtech.no. My name is Roy Borgen, and I'm ShieldTech's founder and Chief Executive Officer. I'll catch you in the next lesson.